to introduce today's speaker. Dr. James Bowen received a Bachelor of Science in History from the University of Idaho in May 2000. A Navy ROTC student, Bowen was commissioned as an officer in the US Navy upon graduation. He completed Navy nuclear propulsion training and served 3 years on the USS Memphis, a Los Angeles class fast attack submarine, followed by 2 years at the Naval Submarine Support Command, Pearl Harbor. Following his release from active duty in 2006, Dr. Bowen continued his naval service as a drill reservist, plus a brief recall to active duty at various locations. Having become interested in further studies in nuclear physics as a result of his nuclear power background, Bowen began pursuing undergraduate studies in physics, receiving a Bachelor of Science in Physics from the University of Idaho in 2008. He subsequently completed a master's in physics at Iowa State University in 2011, and it was there that he first became involved in experiments in high-energy nuclear physics, participating in the Phoenix experiment at the Brookhaven National Laboratory. He began PhD studies in experimental high-energy nuclear physics at the University of Kansas in 2011, where he joined the CMS experiment collaboration at CERN, graduating with a PhD in 2018. Dr. Bowen subsequently worked at the Naval Oceanographic Office as a civilian physicist from 2018 to 2021, where he worked on efforts in ocean acoustics and participated in oceanographic surveys. He returned to Kansas in 2022 when he assumed his current position at Baker University. Now let's get ready to explore heavy ion collisions with Dr. Bowen.
All right. Good morning, everybody. First of all, can everybody see my screen?
Yep.
All right. Okay. So, thank you very much for the introduction there, Dr. Heiss. So what I'm going to be talking about today, I'm going to be talking about the research that my research group at the University of Kansas has been working on. One of the things we've been working on anyway. It's measuring dijets from ultra-peripheral heavy ion collisions. This is what I did my dissertation on at Kansas, and it was a major undertaking of our group for several years. I'll talk a little bit more about the timeline as the presentation goes on of how this went about. But in the meantime, let's get going. Okay, so collisions of high energy heavy nuclides have been conducted at the relativistic heavy ion collider or RHIC for short since the year 2000, and since at the Large Hadron Collider at CERN since 2010. We believe what's happening is when these nuclei collide, they form a quark-gluon plasma. We think that the protons and neutrons are melting into a decoupled state of nuclear matter, and I'll talk about that more later, what exactly that means. So, also, hadronic jets from ultra-peripheral collisions, or UPCs for short, are being used to study the gluon distribution in those nuclides before they would otherwise form a quark-gluon plasma in a more central, that is, a head-on collision. And I'll talk more about what these terms mean as we go on here. Okay, so like I said, this presentation focuses on my dissertation research, which itself was part of an overall analysis to analyze these dijets that are produced in these ultra-peripheral heavy ion collisions. And of course, the data was collected by the CMS experiment. We are part of the CMS collaboration, so it's the CMS experiment that collected them. And I will talk about how the CMS experiment is designed and how it works later on in the presentation. So this is the Large Hadron Collider right here. It's located on the Franco-Swiss border near Geneva, Switzerland. So you can see Geneva in the background there where I'm pointing. Um, the main CERN site is right here. It's actually right on the border, the main CERN site is. Um, there's four big experimental detectors on the Large Hadron Collider. There's LHCb, which is near the Geneva airport. There's Alice, which is in a village called Saint-Genis. Um, and then there's Atlas, which is at the main CERN site. And then there's CMS, which is all the way out here. Like complete opposite side of the ring from the main site, which meant it was always I always had to take a shuttle to get there. um, okay, and then of course this is the Previs where I'm pointing right here. That's the Previson site right there. That's where the collider is controlled from. All right, so the purpose of the heavy ion physics program is to understand the strong nuclear force at very high energy and density. Um, I would say that the strong nuclear force at this point is probably the most mysterious of the four fundamental forces of nature that we know of, in the sense that we don't fully understand how it works. We have a very good understanding of how electromagnetism and gravitation work. The weak nuclear force, that one's a little stranger, but I would say our picture of that is even that one is more complete than it is for the strong nuclear force. Um, so like I said earlier, there's evidence for the formation of a decoupled state of nuclear matter called a quark-gluon plasma following collisions of high energy heavy ions. Um, First of all, before I go any further, let me talk about the theory of quantum chromodynamics. This is our theory for how the strong nuclear force works. In the strong nuclear force, color plays the role of charge in electricity. Now, but unlike electromagnetism, where there's six colors, for the strong or two charges, for the strong nuclear force, there are six colors, and we call them red and anti-red, blue and anti-blue, green and anti-green. And the reason why we call them colors and why we call this strong version of charge color is because color neutral configurations include any color paired with its anti-color or the combination of the three colors or the three anti-colors. So that's analogous to how if you combine red, blue, and green, red light, blue light, and green light, you get white light. So it's kind of, that's why we call it color. It really has nothing to do with real color. It's just an analogy. That's all it is. And the color and an anti-color, that's very similar to electromagnetism, where you have positive and negative charges. But the interesting thing about the strong nuclear force is that a combination of three colors or their anti-color counterparts will also give you a color neutral configuration. So now let me talk about hadrons. Hadrons are made of partons. In other words, quarks and gluons. Now, quarks are fermions that interact strongly and electromagnetically. That is, they possess color and charge. They also interact by the weak nuclear force, but I'm not really going to focus on that here in this presentation. They generally consist of what we call three valence quarks. Those are the baryons, or three valence antiquarks. Those are the antibaryons, or valence quark antiquark pairs, and we call those mesons. So the quarks have three colors to make a color neutral configuration: red, white, and green. The antibaryons, they have anti-red, anti-blue, and anti-green to be color neutral. And then the mesons, they have a quark antiquark pair. Um, now, evidence for exotic mesons, that is, two quarks and two antiquarks, and exotic baryons, which consist of four quarks and one antiquark, has emerged in the last 10 years. Um, now, hadrons also consist of what we call C-quarks and gluons. C-quarks are quark-antiquark pairs that 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 basically form by means of pair production from gluons. Now, all hadrons are color neutral. Just like an atom is charge neutral, all hadrons are color neutral. Okay, so now let me talk about gluons. Gluons are the mediators of the strong nuclear force. They're analogous to photons in electromagnetism. Um, but here's a big difference from electromagnetism. Unlike chargeless photons, gluons themselves possess color and interact with other gluons. Um, each gluon possesses one color and one anticolor. And this results in specific flavors of quarks changing color upon interacting with another quark. Um, Gluons also change color upon interacting strongly. Now, and this stands in very stark contrast to electromagnetism, where the charges are fixed. Now, what I just told you, the fact that the gluons themselves possess the mediators of interactions between the particles with color themselves possess color, that makes the strong nuclear force a much more complicated force dynamically than the electromagnetic force is. Um, Okay, so here's some graphics that show basically what I'm talking about. For a baryon, uh, a red, blue, and green combination. Remember, we have six colors. We have six colors plus red, blue, and green plus anti-red, anti-blue, and anti-green. Well, in a baryon, red, blue, and green give you a neutral configuration. That's this white here in the middle. An anti-baryon, very similar. Um, and then a meson, say we have a red and a quark with a red color charge and an anti-quark with an anti-red color charge. When they combine, they make a color neutral configuration as well. And the graphic on the right here shows gluon exchange, and it shows how quarks, when they exchange gluons, how they themselves change color. Okay, so based on what I just told you, this is what this so far as we've been able to measure, this is what the interior of a proton looks like. We have our valence quarks here. It consists of two quarks that we call up quarks and one quark that we call a down quark. Now, there's six types of quarks plus their anti-quark pairs. But the protons and the neutrons that make the building blocks of the hadrons that the of pretty much all baryonic matter that we observe in the universe. Um, it's up and down quarks. Like a proton, it's two up quarks and a down quark for the valence quarks. Um, and for a neutron, it's two down quarks and an up quark. Um, and these spring-like things you see, these are the gluons, and these pairs of quark anti-quark pairs in here, these are the C quarks that are produced from pair production of gluons that exist in a hadron. Um, and the arrows you see, that indicates the spin of each of these particles. Quarks are fermions, so they have a half integer spin, and gluons are bosons, so they have integer spin. Any questions so far? Okay. Um, Next. So the now the strong force between quarks increases if we pull quarks further apart. Um, at about 1 Fermi, that is about 10 to the minus 15th meters of separation, a new quark and antiquark pair will be formed, which actually increases the number of hadrons. So if you put enough energy into quarks to separate them by about 1 Fermi, you're going to get a new quark antiquark pair that basically pops into existence. The energetic conditions are at that point are permissive for just new particles to form out of the vacuum. Um, The cascading of this process results in jets, with each jet running along the original direction of the quark antiquark pair. Um, so this is a Feynman diagram of a jet right here. So this is jet one right here. This is jet two. The straight lines are quarks with arrows, quarks and antiquarks. The spring-like lines are gluons. And notice that the jets at some point do have to be connected before they go off in separate directions, such that color will be conserved. Just like charge and electromagnetism, color is a conserved quantity. All right. So this is an example of a detection of a dijet in the CMS experiment. This particular one was detected in July of 2012. So what we were looking for in this experiment looks a lot like this right here. Okay, so like I said earlier, at RIC and the LHC, heavy nuclei are being collided at energies that result in the formation of a quark-gluon plasma. So I just told you about baryons and mesons. Under these conditions, the baryons and the mesons will melt. And the medium behaves like, at that point, the medium behaves like a dense fluid of unbound but strongly interacting quarks and gluons. So it's often compared to a phase transition where you if where the hadron is the solid state and the quark gluon plasma is the liquid state. Um, the initial state before the formation is of interest, and that's what this research that I'm talking to you about today focuses on. It can be studied by deep inelastic scattering or photon nucleus collisions. Um, so this is a phase diagram of nuclear matter right here. Um, the hadrons right here, this is the existence that we're familiar with. This is what protons and neutrons are, as well as the mesons that protons and neutrons interact with each other with inside an atomic nucleus. Um, but if you go to high enough energies, you get the formation of a quark-gluon plasma, where we go to this more liquid-like phase. Um, these ovals right here highlight the ranges of this phase diagram where Rick and the LHC can explore. Um, so and over here you'll see something called color superconductor. I'm not going to talk much about this today, other than on this slide, but this is kind of interesting. We think that this might be what happens right before matter collapses into a black hole, but that's where quarks actually start to form Cooper pairs with each other, and therefore that's why they call it a superconductor. Okay, so some useful quantities I should define for you. Bjorken X is the ratio of parton momentum and hadron momentum. And Q is the momentum that's transferred to a parton when it's struck by an incoming object. So a measurement of dijets from ultra-peripheral collisions can yield a distribution of X and Q for gluons in a pre-collision nuclide, which enables us to study that initial state that I was talking about a moment ago. Okay, we also need to take advantage of relativistic invariance to do this experimental analysis. So these right here are the relativistic invariants. And notice that Bjorken X is equal to T divided by S, which is also equal to momentum transferred squared divided by S. I should also tell you that I should also define PT here. PT is the perpendicular component of a of the momentum of a collision produced particle with respect to the beam, and PZ is the parallel component. Okay, So the total momentum of all partons in a hadron must add up to the momentum of the hadron. Um, and like I said, this can be studied by deep inelastic scattering. That picture of the proton I showed you a few minutes ago and that I have pictured again here, this was all learned through deep inelastic scattering. Um, so how deep inelastic scattering works is, so like, say we use a charged particle like an electron, and when an electron approaches a hadron, it exchanges a gamma ray with one of the partons, and that parton, or that gamma ray, then will cause changes to the hadron. But we can use the results of that to map we can use the results of that to map out the interior of a hadron. So it's yeah, so we just basically long story short, we scatter electrons off of hadrons, and the higher the energy of the electron, the more, because of the de Broglie wavelength, the more resolute detail we can see inside the hadron. So this is the parton distribution function for the proton right here. This was obtained from the Hera experiment. The Hera experiment ran at the German electron synchrotron in I believe it's in Hamburg. Yes, it's in Hamburg. From 1992 to 2007. And so what we found was at very high values of X are dominated by the valence quarks, the up and the down quark. And as you can see, there's twice as much X for the up quark as there is for the down quark. Remember when I showed you there's two up quarks and a down quark for valence quarks and a proton. So that's what's to be expected. But notice as we get to these smaller values of X that that the number of C quarks goes way up, and the number of gluons goes up even more steeply. Like this is just 1/10 of the gluon parton distribution function right here. Um, so that's very interesting. But we know that the higher gluon density must reach saturation and reverse at some point, because the number of gluons are is basically it's the number of gluons is inside the hadron is basically finite. It's not infinite. Um, there's a finite amount of energy, so there's a finite number of gluons in there. Um, so an accelerator with x and q squared ranges beyond Hera is needed for further investigation. Um, the electron ion collider, which is now, just as we speak, is now starting construction and conversion from RHIC at Brookhaven, will continue where Hera left off. But in the meantime, the use of ultra-peripheral collisions at the LHC for heavy ions that otherwise form a quark-gluon plasma at more central collisions can be used for this purpose. And the LHC is especially useful for this because RHIC is a considerably lower energy machine than the LHC is. So these gamma rays, and I'll talk about this in a few minutes here, but these gamma rays that cause these ultra-peripheral collisions, they're much higher energy at the LHC than they are at RHIC. Okay, so this is the X and Q squared coverage of the comparing the SPS, the RHIC, and the LHC. And this parallelogram right here, this shows the range over which we can use the jets from ultra-peripheral heavy ion collisions at the LHC to analyze. Okay, so let's talk a little bit about photon nucleus collisions. So I just talked about a ring of gamma rays surrounding the nucleus. This is why we have a ring of gamma rays surrounding a high energy heavy ion. So when the speed of a lead nuclide in the lab frame approaches that of light, its electromagnetic fields resemble those of propagating electromagnetic waves. Um, for a lead nucleus that's traveling at this speed that's very, very close to the speed of light, which is what's happening at the LHC, these fields can be modeled as a flux of almost real photons surrounding the fast-moving nuclide. The nucleus is moving almost at the speed of light, so these are virtual photons, but we can say, for all intents and purposes, that they're real. Um, in an ultra-peripheral collision, the other nuclide will pass through this flux and might be hit by these photons. Quantum field fluctuations result in photons transforming into quark or gluon pairs, which interact with gluons in the nucleus. Vector mesons, open heavy flavor mesons, or jets can be produced. And the results can be used to probe the initial state and search for gluon saturation. So this is just a diagram that shows you what's going on. It shows you one of these gamma rays that surround the high energy heavy ion. It interacts. It passes through a nearby passing heavy nucleon in the other direction, and quantum field fluctuations cause it to undergo a strong reaction inside, and which results in two jets, what we call dijets. So, as far as measuring these go, this was first proposed in a paper that was written by three theorists in our field: Ramona Vogt, Mark Strickman, and Sebastian White in 2006. The successful measure of these UPC dijets was projected to possibly lead to a better understanding of the distribution of quarks and gluons inside the lead nucleus before it collides. So our research group at KU, while this was analysis in progress, we switched our focus to azimuthal correlations between the total transverse momentum of the dijets and the momentum difference of the dijets in order to examine the gluon correlation in the nucleus. Essentially, we were looking for signs of bound states between gluons. So this is a Feynman diagram of a reaction that produces a UPC or produces a UPC jet. So we have a gluon. We have one of these gluon. I'm sorry. We have one of these photons, ring of photons from one nucleus that passes into the other nucleus. And like I said, it undergoes quantum field fluctuations and results in a pair production of two quarks. One of those quarks will then go on to interact with a gluon inside of there. And when that happens, what results is these jets of strongly interacting particles that and the jets are a result of what I told you earlier. The reason why we get these jets is that there's so much energy here that these quarks are ripped apart from each other by this energetic reaction, which goes on to form beyond a distance of 1 Fermi. It goes on to produce more quarks. And so as a result, we get two jets of hadrons. So the momentum of the jets can be measured by the CMS detector. X and Q can then be determined if photon direction is known. Photon direction ambiguity can be resolved when one nucleus breaks up, that nucleus being the one that absorbs the photon. Now, nuclei are normally bound on the order of a few MeV, million electron volts, but these high energy photons that surround these nuclei, they typically have energies in the billion or giga electron volts range. So so a nucleus is highly unlikely to remain intact after absorbing one of these gammas. It's also useful to define rapidity. Rapidity is it's essentially an energy and momentum measurement using energy and longitudinal momentum. But what's useful about it is that it's relativistically invariant. And of course, beta here is just our beta factor from relativity, which is speed divided by the speed of light. And so this isn't going to quite be 1, but it'll be, for these reactions, it's pretty close to 1. Um, Now, pseudo rapidity is a geometric measurement. It's equal to the negative log of the tangent of the angle with respect to the beam line divided by 2. But when at very, very high kinetic energies, when our kinetic energy is much higher than our rest mass, the pseudo rapidity is approximately equal to the rapidity, which makes analysis easy. That's actually very convenient for our analysis. Okay, so there's going to be 2 Bjorken X's that result from this. This is the formula for the first one right here, and this is the formula for the second one. Now, at first we don't know which one's the photon and which one's the gluon, but the experimental setup can resolve that ambiguity. And Q then is going to be the square root of the X for the photon times a relativistic invariant S. So this is the CMS detector right here. It is a very large detector. It is about the size of a World War II Alaska class battle cruiser. It consists of several subsystems. The innermost, so right here where I'm pointing, this is the beam pipe where the collisions take place, where the high energy nuclear reactions take place. The most central portion right here, these are the silicon trackers. These track charged particles. This green layer right here, that is the electromagnetic calorimeter. It measures the energy of electrons, positrons, and photons. This gold layer, this kind of gold colored layer right here, that is the hadronic calorimeter. That measures the energy of hadrons, like high energy protons, neutrons. You'll get some mesons, like pi mesons might make it to there as well before they decay. This right here is the superconducting solenoid. So this is a solenoid that produces a 3.8 Tesla magnetic field. And that 3.8 Tesla magnetic field is what allows us to measure the momentum of charged particles in the tracker and in the muon chambers, which is out here. Now, these are the muon chambers out here. The muon chambers are they're resistive plate chambers. I mean, you could kind of think of them as very fancy Geiger counters. The muons do not interact with hadronic matter at all. Well, okay, they interact electrically, but not strongly. So therefore, they're going to pass right through through the hadronic calorimeter, and they're going to leave tracks in the resistant plate chambers, and the curvature of those tracks produced by the magnetic field allows us to measure the momentum of the muons. Now, we didn't use the muon chambers, the muon trackers for this experiment, but since it is called the Compact Muon Solenoid, I thought I should mention that. And then we also have the 0-degree calorimeters, the 0-degree ZDC plus and the ZDC minus. They are 140 meters away from this point right here on each end. So 140 meters this way, 140 meters this way, outside the main part of the detector. And what the ZDCs do is they measure neutral particles that come out of these collisions that continue down the beam line. Because when the beams eventually separate back into 2 tracks by the superconducting magnets that steer the particles in the collider, these neutral particles, they're not going to be steered. They're just going to keep going. So that ZDC intercepts them and detects them. Okay, so this is the coordinate system for the ZDC right here. This is our theta angle right here. And remember, this is the relationship between pseudo rapidity and theta right here. So basically we can think of pseudo rapidity is how far it is off the beam line. You can think of it as being related to theta. So this right here is a diagram of how particles are detected. Um, I would spend some more time on this, but we are kind of, we are on the clock here, so I'll very quickly show you what happens. Um, Electrons and photons get absorbed by by the ecal, the electromagnetic calorimeter. Hadrons get absorbed by the hcal. And charged particles get steered by the magnetic field. They get diverted by the magnetic field, which allows in the tracker, which allows us to measure their momentum. And as do muons. And then muons will continue on to the muon trackers, where they will also be diverted by the magnetic field. Okay, and so this right here, I talked about the jet clustering algorithm. This is basically a computer program that classifies jets. When a jet is produced, there's a computer program that classifies detections as jets. Um, and this is what it looks like right here. It's a clustering algorithm. That's what it is. Um, okay, so a dijet has it has two back-to-back jets in CMS, and then there's an imbalance of neutrons between the ZDC plus and the ZDC minus. And then there's a pseudo rapidity gap, meaning that there should be nothing in one HF calorimeter. So now let me go back here a little bit. The HF calorimeter, that's this thing right here. This is it's part of the hadronic calorimeter, but it's forward. It's in this region right here. Okay, now also I need to talk about triggering. So we used an electromagnetic calorimeter detection of at least 5 GeV from a single particle hit. This serves as our jet trigger, since UPC jets are likely to deposit at least 5 GeV in the ecal. And we didn't use our dedicated our pre-programmed jet triggers because they have low efficiency for below 60 G for a PT of below 60 GeV per C. Um, Also, we wanted to make sure that energy is measured exclusively in one HF calorimeter and not both. That's indicative of that rapidity gap that I was talking about. And then at least one pixel track is measured, because a UPC jet should have at least one charged hadron in it. So the data was collected in December of 2015. And this 5.02 TeV per nucleon was the center of mass energy between these in these collisions right here. So what we saw then is we did see dijets. These are the dijets that we saw right here, and this is their angular azimuthal separation. Um, and this is the transverse momentum of these dijets. So we organized it into leading jets, that's in the red right here, and subleading jets. So we paired a jet with one that was that occurred at the same time and was very close in energy. And PT. Um, okay, so um we so this was our average rapidity right here. So notice that we have a trough at 0 and then peaks on either side. That's indicative of those are indicative of the rapidity gaps that we were looking for. And that manifests itself in the ZDC detections as a that manifests itself in the ZD in the ZDCs as a detection in one ZDC without a detection in the other one. So if we sum all these up, this is what the rapidity average looks like, and we get an L-shaped plot on the ZDC when we sum all them together. Okay, so we require that the timing of the ZDC signal be consistent with a real interaction and not with noise. calorimeters tend to be very noisy devices electronically. And we also required the ZDC end in question to have a signal of more than 500 FC. So again, like I said, calorimeters tend to be noisy. So this is to screen out noise right here. All right, so this is what we found right here. When we looked only at one side, we saw eta was the rapidity was strongly biased towards one end, and we saw ZDC, we saw the detections on one ZDC but not the other one. And then when we looked at the other end, we saw the opposite, which is which is indicative of a dijet. Now there were sometimes both sometimes there would both nuclei would break up, so those were more complicated to analyze. But this was very indicative of what we saw, of what we were looking for. I mean, okay, so it was also useful to compare ZDC and HF because the HF is in a very forward location, and the likelihood of nuclear that nuclear breakup was detected by the ZDC would also be detected by the HF on the corresponding HF. So we looked specifically for these were some more screening criteria we had, so to speak. We looked for greater than 5 GeV in one and less than 5 GeV in the other. And this is what we saw. And again, very, very similar to what we saw with the ZDCs. And so this is ZDC distributions versus Dijet rapidity. This was shown on an earlier graph, so just here it is again, a bigger picture of it. Okay, so this is then so therefore we were able to resolve the ambiguity, like we said, like I was saying. So this is what we saw then here was that in this case X1 was the gluon X, and X2 was the photon X. Notice that, and down here X1 was the photon X and X2 was the gluon X. Now notice that what this means, given the location of these the location of eta and so forth, of the average eta of the Dijets, what this tells us is that the gluon energy was usually higher than the photon energy, but not always. And this is just showing the same thing with HF right here. So, like I said earlier, we did switch the focus to our analysis because while our analysis was in progress, a theoretical paper came out that suggested that the exclusive Dijet vector sum and vector difference is sensitive to angular correlation between gluons. Such correlations indicate that gluon pairs form bound states with orbital angular momentum. So our group decided to specifically focus on this analysis. And here's the Feynman diagram of the process. Basically, the important point here is that no net color is exchanged. It's a gluon pair where no net color is exchanged. So and here I define the rapidity gap. Okay, so we had forward rapidity gap dominant events, and we had backward rapidity gap dominant events. That's what this plot is showing right here. These are the forward dominant rapidity gap dominant. These are the backward rapidity gap dominant. And again, here's another eta average of the this is the backward dominant, this is the forward dominant right here, comparing them to these histograms that I have. And these are and it's also important to define capital QT and capital PT. So that the PT of the jets, capital PT is this PT of the leading jet minus the PT of the subjet leading jet divided by 2, and Q is the sum of both their PTs. And what's important here is this angle phi, the angle between between 2 times pt and qt. Um, okay, so this is a plot of qt, capital QT and capital PT right here for the events we looked at. And so what we were looking for is a raw distribution of phi. Now, a zero angular correlation, for a zero angular correlation, there would have been nothing special about this graph right here. It would have just been like a straight, it would have just been roughly similar levels across this histogram. But we see here from the plot of these events versus their events versus phi that is not the case. That there clearly are angular correlations here, as summed up by this factor that we call V2 here. So V2, um, this is a quick plot of V2 and for our QT ranges and our PT ranges. In all cases, the systematic the results and their systematic uncertainties clearly exceed 1, which shows that there is a positive angular correlation. So our conclusions are that UPC dijets that are symmetric in eta have been detected. X and Q for UPC photons and gluons have been measured. A positive angular correlation, that is a positive V2 signal, is present for the dijets. The latter indicates that each gluon in the gluon pairs that interact with photons in the UPCs to produce the dijets are correlated with each other. In other words, this is evidence that gluons form bound states with each other. Okay, so here's a list of my references right here. Now, notice that, remember when I said we took this data? We took this data in late 2015. Well, as a measure of how things how the timeline of things progress at CMS, the paper was published in August of 2023. All right. So at this point, that is the conclusion of my presentation. So if anyone has questions, I'll be happy to answer them.
Thank you, Dr. Bowen, for that fascinating presentation. Any questions? Let's see here. Here's one. Regarding the search for supersymmetry at the LHC and the motivation, is there a motivation for the new 100-kilometer circumference FCC, the future circular collider at CERN? I don't know if you can comment on the physics program there with the future of CERN coming up.
Okay, so that's a great question. My background is in experimental high energy nuclear physics. So as far as the theoretical background goes, I cannot think of anything specifically that would that there are any specific theoretical targets that the FCC would address. I mean, it would be very interesting to build it and see what happens, but such a machine is going to be very expensive. So I know that the people who pay for this, which are the people who pay taxes in the supporting countries, would probably want a concrete justification for this. So so the answer is I can't think of anything specifically. I think it would be very interesting to do the type of research what I was just talking about with that collider. I mean, with those kind of gamma rays, let's first see what the I say let's first see what the EIC at Brookhaven gives us. So it's let's see what that does for us first. Personally, as a physicist, I would like to see the future circular collider built, but I cannot think of any specific theoretical targets. And you mentioned supersymmetry. The results from the LHC have not been let's just say they haven't been promising. They have not been friendly to the supersymmetric theories. So maybe the FCC would allow some of those more unlikely windows that the LHC is incapable of searching to be searched. So maybe there is that. Maybe the FCC could give us a final verdict on supersymmetry.
Fair enough. Yep, that would certainly be exciting.
Yes.
You mentioned earlier in your presentation about the quark-gluon plasma, and I'm trying to remember, there was some connection to the black hole formation. Is there any evidence in nature beyond the accelerator physics that you were describing for quark-gluon plasma?
Okay, so that's a very good question. Quark-gluon plasma is we believe that in the moments after the Big Bang, the entire universe was filled with a quark-gluon plasma. So I said that we do these experiments to study the strong nuclear force, but there are also cosmological implications to studying the quark-gluon plasma. Did that answer your question?
Yeah, no, absolutely. That's a
Okay.
good point.
Yeah, so we've detected it in our colliders, but we think that the moments after the Big Bang, we think that all of the strongly interacting matter in the universe was briefly a quark-gluon plasma.
Is there any association with the formation of a black hole, or was that some other reference?
Oh, okay, so that I think what you're probably thinking of there is the color superconductor.
Oh, sure.
Yes, so we think what happens is that in very, very, very dense nuclear matter, we think that the quarks start to form Cooper pairs. And that would happen under extremely dense conditions, like a neutron, like a very dense, like at the core of a neutron star that might be on the verge of collapsing into a black hole or something like that.
Mm. Yeah. Yep. That makes sense.
Yeah.
Another question here. Oh, sorry.
I was going to say both very energetic and very dense conditions.
Mm. Question here. CERN posted an article on a new Nature publication with the title "Observations of the Formation of Light Nuclei from High Energy Collisions that Might Help in the Hunt for Dark Matter." So light nuclei shedding light on dark matter at some of these large collider laboratories. Is there any connection between your research and how quarks and gluons are involved and maybe a connection to dark matter?
There may well be. If there is, I haven't been involved in it. I am a little bit familiar with the formation of light nuclei. At the star experiment at RIC, they that one of the things the star experiment looked at was the formation of anti-alpha particles of antimatter helium nuclei. So that so we have done a little bit of that, but I'm not really familiar with how that relates to dark matter.
Sure. Mm-hmm. Another question here. So you mentioned the electron ion collider, the EIC. That's basically the nuclear physics equivalent to the LBNF Dune project in terms of priority, also in terms of cost, several $1 billion. That you mentioned that would carry on the work that you've been interested in particular. Maybe just say a few more words about the science program of the EIC and how it relates to things you're interested in.
Okay, so remember when I showed you when I was talking about deep and elastic scattering? So the type of work I was doing is kind of a substitute for deep and elastic scattering. We're using high energy gamma rays as opposed to high energy electrons to probe the interior of high energy nuclei. So what the electron ion collider is going to do, it's going to collide heavy ions with electrons. And these electrons, they'll be able to control the input energy of these electrons. So they'll be able to control the energy of the electrons that they collide. So therefore, Therefore, remember when I was talking about Q, the momentum transferred between particles in these reactions. They will be able to control Q at the EIC. Whereas in that's the advantage of having the electron ion collider. In this research that I did, we just kind of had to take what we were given, because those gamma rays, those high energy gamma rays that surround the nuclei, they are what they are, and we'll it's kind of like we'll take what we can get, but at the LHC we can control not the LHC, the EIC. We can control the parameters of the experiment better than we can at the in ultra-peripheral heavy ion collisions. Not that ultra-peripheral heavy ion collisions aren't interesting or useful, but we are kind of at the mercy of quantum field theory there.
Very good. All right. I don't see any other questions, and we're getting close to the top of the hour. So why don't we go ahead and wrap up?
Okay.
So just a reminder to our audience, this talk is available to view and share on YouTube, Vimeo, and our Institute website, institute.surf/deeper-talks. Next month's Deeper Talks will be on January 14th at our standard time, 9 a.m. Mountain. And the topic is the impossibility of a neutrino laser, with featured speaker Dr. Joe Formaggio. As always, your feedback helps improve this program, and we appreciate any suggestions for speakers and topics for future talks. Please fill out the short survey you'll receive immediately following the talk on Zoom and in your